Hey guys, let's try a cliff problem. All right? So this is a classic physics problem, and the question basically always is how far from the base of the cliff will the object land? All right, so how do we figure that out? Well, what I would always recommend is do this in your head a little bit before you do anything on the paper. Get an idea of what's going to happen. So our first understanding, we really should just briefly look at a free body diagram of this. So here's a free body diagram of it. Once it's been projected, it's not being touched anymore, it's just in the air. What does this object look like when it's in the air from a free body diagram perspective? Does it have any horizontal forces on it? Not after it's been accelerated to 2 meters per second and then let go. So there's no horizontal forces. Yeah, there's a tiny bit of air friction, but we can ignore that. So there's no horizontal forces. What's the vertical forces on it? Well, we have the object's, what would you call this? Don't say gravity. This is the object's weight, mass times gravity. Are there any upward forces? Is there a normal force on this? Well, not once it's off the edge of the cliff and it's in midair. So this is the free body diagram of the object when it's in midair. Why do we need this? Well, what that means is this object is going to be accelerating in the vertical position or in the vertical direction, and it's going to be moving at constant velocity in the horizontal direction. So if we have a cliff 125 meters tall, can we use our drop problem abilities to hone in on how long this object is going to take to fall? Because I think you recognize that what's going to stop it from its continuous 2 meter per second motion forward is going to be when it hits the ground. So the question simply is, when is it going to hit the ground? Well, drop problems. Why don't we try 3 seconds? 3 seconds. You start at 0 meters per second, end at 30 meters per second. Average is 15 meters per second. For 3 seconds gives you 45 meters. This is more than that. 4-second drop problem. Start at, end at, average times 4 seconds gives you 80 meters. Hope you're keeping up. Okay, this is more than that. How about a 5-second drop problem? Starts at, ends at, average times 5 seconds gives you 125. So we know this is going to be falling for 5 seconds. Each one of those seconds, it's going to be moving 2 meters further from the base of the cliff. So you could come up with it's going to be about 10 meters from the base of the cliff. So that's what we know the answer to be, approximately. And of course, I made it a very simple problem, but you could still get an approximation of the answer with some very simple mathematics like that. Drop problem, and then multiplied the number of seconds it would fall about times how fast it's going. But to do it formally, we have to break it into horizontal and vertical. Well, which should we do first? Well, we have to find the time of flight first. Then when we multiply the time of flight by the horizontal velocity, we'll get the distance. So to find the time of flight, we need vertical givens. So let's see, what do we have vertically? Well, we know that it's going to be accelerating, and that acceleration is going to be gravitational acceleration. Great. We know the distance. The distance is 125 meters. We know we're looking for the time, but there has to be one other given because these don't relate without one other given. And sure enough, the other given is our initial velocity. Now let's think for a second. What is our initial velocity in the vertical direction? We know in horizontal it's 2 meters per second. But what is it in the vertical? Well, it's not being pushed up. It's not being pushed down. There's no aspect of a vector direction in the vertical. So our initial velocity is 0 meters per second. That's going to be important. What formula would we use here? Well, we have these 4 variables, and we can connect them. Like any good physicist, we would simply go to our book of proven formula, and whatever we need, we would look at the variables we have and try to find what we need from those proven formula. You have your reference table. And in there it says d equals VIT plus 1/2 AT squared. Well, that VI is 0 meters per second. Therefore, the formula becomes d equals 1/2 AT squared. We're solving this for t, so how do I get rid of all this other stuff? To get rid of the 1/2, we have 2d. To get rid of the a, we divide by a. To get rid of the t squared, we take the square root. By the way, taking the square root, that's one place we tend to mess up. Anytime you're taking a square or a square root, that's where you can mess up. How do you protect yourself from that? Hope you said units. S and S. So we got t equals square root of 2d over a equals square root of 2 times 125 meters over 9.8 meters per second squared. Before we go any further, how are the units going to work? Well, this is going to come up and be seconds squared over meters. The meters are going to cancel, leaving me with seconds squared. But I'm taking the square root of it, so that'll turn it back to seconds. So this looks good. We just checked our algebra. And when we do this then, 2 times 125 divided by 9.8 equals 25.5. There you go, 25.5. Is that right? Now, wait a second. Didn't we say it was going to take 5 seconds to fall? Huh. What did I do wrong? Look at that. The square. I have to take the square root of that. Listen, you'll make that problem. You'll always make that mistake, or you'll often make that mistake. Use your units. Please use your units to watch that. Use your initial understanding of a problem before you just jump into it. Very often you can really get a sense of what the problem should be. That's a mistake that anybody can make, but I shouldn't see it too often. So this is approximately 5.1, but I'm going to leave the entire number there because I think it's always best to round external to the problem, not internal to the problem. So keep the numbers going. So our givens here, these are our givens horizontal. So time equals 5.1 seconds. The seconds squared. We took the square root. Time is 5.1 seconds. So our first given is t equals 5.1 seconds. Our velocity. Do I need to say initial, final, or any other kind of velocity? Well, our free body diagram shows there's no acceleration in this direction, so that velocity is just a velocity. It's going to stay at 2 meters per second. What are we looking for? We're looking now for the distance. And because there's no acceleration, our formula is going to be the nice, easy v equals d over t. D equals, well, multiply both sides by t. D equals v times t. And again, we'll check that in the algebra. D equals v times t equals 2 meters per second times 5.1 seconds. Well, what does that equal? Because I have the number in here, and that's the real number, when I multiply that times 2, all right, so I get 10.1, well, the seconds, cancel the seconds, 10.1 meters. Am I looking for meters? I am. Can I say 10.1? Well, what are my significant figures here? I have 2 as the number of my meters per second, not 2.0, just 2. So does that justify 3 significant figures? It certainly does not. So best I could really say is 10 meters. So that is my cliff problem. I hope you see. You find out how long it's going to take to fall. You multiply that time by your velocity, which is going to be constant. And the neat part about this is there's 2 different things happening in each of these. So we have a vertical for the accelerated component and a horizontal for the non-accelerated component. We need the time it's going to take that time, multiply it by the velocity. That's all there is to it, but it's definitely a little bit of physics understanding. Hope you got a lot out of that. I know I did. Thanks for watching.